Hi everyone, this is Chapter 9, Phase Diagrams. In this chapter, we're going to look at the big picture question of when we put two elements together, let's say two, and then the question is what is the equilibrium state of that material? What do we get, right? We can answer all kinds of questions. If we have a composition, like for example, if we know how much copper and nickel we have, and we know the temperature, then can we know what type of structure it has? Do we know if all the material has the same structure? Can it change to a different structure? You know, we can reword some of these questions and ask even more. Basically, how many phases form? How many phases of that material form, and what is the composition of each of those phases? What is the amount of each phase? Here on the bottom, we have nickel and copper shown as gray dot and orange dot, and you can see that you can arrange these atoms in a lot of different ways, and perhaps the one over here on the left with the gray square, gray rectangle is phase A if it's arranged in this order. But if it's arranged in, straight rows, perhaps that's a different phase. So it's the same materials, the same atoms, but we can rearrange them. And can you have multiple phases? How do you know how many different kinds you can have? These are some of the questions we're going to be answering. Really, I should say starting to answer. Okay, so let's move on. You might be asking at this point, hey, are we talking about mixtures? And I would say yes. Everything that you've learned about mixtures from chemistry applies and more. Okay, so we should probably define our terms at this point. Because if I were you, I would have been asking, what's a phase? All right, we have two terms here. We have the term components and phase. So these are outlined in red. There are definition words you need to know. The elements are the compounds which are present in the alloy. Okay, those are the compounds. Which atoms are present? Those are components. The phase looks at the way that those are put together. It's the physical and chemically distinct material regions. Physically and chemically distinct material regions. Okay, so you may have, often we use these letters alpha and beta to designate different phases, ways that these atoms can come together. So this is, we can start to see these things using microscopy, and this is an example of beta phase being the light gray in this aluminum copper alloy, and alpha being the darker phase. You can see that they arrange in different, in different types of organization systems with different percentages. How many are there? Okay. Now that we've defined phases and components, we want to look at how we transition from one to another. Okay, this is something you've done many times in chemistry or physics, looking at solutions and mixtures. Solutions being a solid, a liquid, or gas solutions. Those have one phase and they are all together and it's pretty homogeneous. But a mixture is when there are distinct locations within a given object or a given material that are distinctly different. Concrete is a phenomenally great example of a mixture, right? You have the aggregates, and if you cut them open, you can see it, and that's very different from the cement paste. Okay, so this is our example, sugar and water phase diagram that we have here, that when you put sugar into water, I should probably be drawing, right? We have a beaker, and we're going to put water in it. And we're going to add sugar, right? We poured sugar in. Ooh, this is a new pen. I don't like it so much. And Yeah, we'll go ahead and get rid of this. Okay, never mind. My pen is not drawing well. We're going to have a solubility limit. That water will take into solution as a lot of sugar to make a sugar syrup. That's the L phase, the liquid phase. But once we reach its maximum capacity to take sugar into the solution, it will be what we call saturated, and then the remaining solid beyond what the maximum value is will remain as solid sugar. Once we move into this side of the phase diagram, we now have a mixture. We have two phases. We have a liquid phase and we have a solid sugar phase. Okay. I'm going to take this another step. The line that separates these two regions represents the solubility limit. It's the maximum concentration for which only a single phase of solution exists, okay? So what we can do is look at the next question, which is what does this mean? Okay? What is the solubility limit? Like how much sugar can water hold, or this liquid syrup hold, in water at 20 degrees Celsius? All right, so the first thing we're going to do, I'm going to use purple. We'll look at our y-axis, which is temperature, and we have our composition percent on the x-axis. So we'll be able to look at both of these. We have a 20% or 20 degrees Celsius line. And so what is the maximum, or what's the solubility limit at 20 degrees? Okay, well, we go over at 20 degrees and we find where on that line is 20 degrees. It's right there. Okay, but what does that mean by saying it's that point right there? You have to define that point in its XY coordinates, okay, where we have X being the composition and Y being the temperature. So at 20 degrees, what is the Y? And we have a value of 65. Our C is 65%. Percent what? Percent sugar by weight. Okay, you can also do percentages, compositions by volume, but we're going to stick with the weight for this time. Let's now look at how some of these systems behave. We'll start with a pretty easy one. What is the effect of temperature and composition? How do those two affect each other? And one thing we can see is that altering the temperature can change the number of phases. We can start with, let's say, here at point B, or A, okay? And if we are at 70 degrees, or I should say 70% sugar, and we're at 20 degrees, then if we heat this up, we could maybe go up to, say, this point. I'm going to switch colors to this. Okay, and I'm going to call this point B, which is now still at 70% sugar, but we're now at maybe 90% or 90 degrees instead of 20. All right, and then let's say we add more sugar. Now, why might we do that? Well, if we've heated up a 70% solution up to, say, 90 degrees or 95 degrees Celsius, and we recognize that we are no longer a saturated solution anymore, and we can actually add more. And so we can, once we add more and come to point C, we're now going to be at maybe 90%. Oh, this pen has to go. maybe 90% sugar, and we're still at the 95. So the point is that altering the temperature can change the number of phases. Over here at A, we have 2 phases present. When we heated it up, we have 1 phase present, and when we then added more sugar, we can have two phases present again. And that's all by altering the temperature. Those are some of the results of the behavior of the system. Now, I'm going to point out that simple systems, and we're still using metal mixtures, do exist as solid solutions where they are completely soluble within each other. This is a good example where nickel and copper are totally soluble within each other. The conditions for which, or the criteria for which you need to that need to exist in order for this system to be completely soluble is you need to have the same crystal structure for both on their own when they're pure. They have to have very similar electronegativities, and their atomic radii need to be very close together. And in this case, these are 2 that will create a really nice simple system. Okay, now we need to start looking at more complex systems that are not just water and sugar. We're going to look at what we call binary phase diagrams. And these are going to be the maps, maybe you could call it, that represent these relationships between the temperature, the composition, and the quantities of phases at the equilibrium. Okay, so I want us to be looking at that. Those are the 3 variables: the composition, the temperature, and the quantity of each phase. All right, and these different factors, varying the temperature or varying the composition or varying the amount of each of the different compositions, will influence the microstructure. And we all know that when you do that, you're influencing the behavior and the structural characteristics of the material. All right, we want to represent this visually so we can see it easily. So we're going to move on and see what these binary phase diagrams look like and how to use them. Okay, we're going to remind ourselves that binary systems are 2 components. We're still looking at metals, so we have our copper-nickel system. It's binary with 2 components. We can see 2 phases in some places, or we have 2 phases, but 3 different phase fields. So our 2 phases are the liquid, L, and the alpha, which is the solid solution, face-centered cubic solid solution. We can say that we have different phase fields by saying this is just how many areas in the graph there are. So for this this white section, when we have these conditions within those areas, you have liquid and solid at the same time. Both of them are present. Now, because this is a binary system, because it happens to be copper-nickel, which we already talked about as being fully soluble with each other, this is also an isomorphous binary phase diagram. Isomorphous meaning it's completely soluble, right? We talked about that, but now we're going to put a word on it, of one component within the other. In this case, our alpha phase field extends from 0 to 100% because it's fully soluble. If it wasn't, then there would be part where our solid phase would end. And again, we have a binary system, meaning that there are 2 components, copper and nickel. Okay, so let's start using these. Our first rule, we're going to go do 3 rules and 3 ways to use these diagrams. First of all, rule number 1, if we know the temperature and the concentration or the percent composition, then we know which phases are present. All right, if we know both the X and the Y, then we know, because we can plot the point, for example, here for B, the 1250 degrees Celsius and the 35% nickel, we can plot that point B and we can see that we're in the white zone. And so we're going to have two phases present. Okay, and then for point A, because it plots down here in this phase field, we have only one phase, which is the solid alpha phase. Okay, so rule 1, if we know the temperature and the concentration, then we know which phases are present. Let's look at rule 2. Rule 2 says, if we know temperature and concentration, then we can not only know which ones are present, but we can determine the composition of each phase. What? Okay, so let's look at an example. Okay, we're going to look at this example. We have several points on a horizontal line, A, B, and D. All right, A and D are the easy ones. So point A is up here in the liquid phase area, in the phase field. And so we know that at 1320 degrees Celsius, not only do we know there's only liquid present, but we can plot this point and say we know that there's 35% nickel. Okay, we know at D is the other really easy point. So these are our two easy ones. At 1250, so we've reduced the temperature. At 1190, only solid is present. So we have one phase, and the percent weight of nickel is still 35%. And you say, well, duh, shouldn't it all be that way? Well, no. The answer is, let's look at B. Point B. Now, because both alpha solid phase and the liquid phase are present, we have to determine, based on this tie line, what the percentage is of each of these different materials, phases. This is called the tie line, and we follow the tie line over. I'm going to switch to purple. We follow the tie line horizontally until it intersects with both the liquidus line, that's what we call it, and the solidus line. Okay, and at that point, for example, of the solidus line, we can find out what the X value is, and we can see that our percent composition of the alpha phase, the solid phase, is 43% by weight nickel. Okay, that's what this one is. And when we go to the left and we intersect with the liquidus line, we can go down, and the intersection is at 32% weight of nickel. All of the material is either transitioning from liquid to solid or solid to liquid, and while there are both phases present, we have a different composition of each of the different materials. The liquid has a lower percent nickel than for A or D, and the solid has a higher percent nickel. That's how you interpret this graph. And we've seen a couple new terminology definitions of liquidus and solidus. Those are two new terms you'll need to be able to use. Okay, so rule 2, if we know temperature and concentration, then we can determine the composition of each phase. So the A and the D were the easy ones, and when you have two phases present, you can use the tie line to determine the composition of each phase. Okay, now let's move on from composition of each phase and look at weight fraction of each phase. Okay, rule 3. If we know temperature and concentration, then we can determine the weight fraction of each phase. Okay, we have our tie line that we've been discussing. And there's a distance or a length for that tie line. We can take 43 and subtract off 432 is 11. And we can look at that and say, well, if we've labeled R and S as distances between the liquidus line and your point of interest and the point of interest and your solidus line, then this 11 is equal to R plus S, right? Okay, so over here, our R plus S is 11, and that's true in both of these different equations. Let's look at this. We want to know the composition for this one at point B, when we have both liquid and solid present, how much of it is liquid, how much of it is solid. And it's simply the ratio of these two values. Okay, so the percent liquid or the ratio of liquid is going to be the solid over R plus S and S over R plus S. And the composition or the weight fraction of the solid is the R over R plus S. This concept is what we call the lever rule. Okay, so let's look at that a little bit more in depth. The lever rule, we use the tie line to connect the phases in the equilibrium with each other. Okay, so we've used this line, and sometimes we call it an isotherm. Okay, so isotherm and tie line are the same. Okay, so now I'm going with my finger, no pen, because that pen was awful. Not sure I like the finger either. Okay, so the question is what fraction of each phase? We're going to look at this as a lever or a teeter-totter, where we have we're going to look at our liquid or our mass of liquid. Let's call that mass or weight fraction of the liquid. Ooh, that's bad. I'm going to just use mass for M. And we have our value R and S. And we will simply use the ratios. We can see that what I'm going to think about is I kind of get the idea that we have a concentration of the solidus here, C sub A alpha and C sub L, and that's kind of our difference between the two, and we're representing that as an R plus S or a M sub L and M sub alpha. And we know that we need to do, say for the mass fraction of the liquid, we need to do either the S or the R part, and the question is which one? And it seems as though, why would you use, the S value instead of the R? Well, maybe one easy way to think about it is if you had B, I'm going to draw a line right here. If B was sitting right in the middle, I would kind of think that that point would indicate that you would have half liquid and half solid. But as you edge closer to the liquid, like point B is closer to the liquid phase, so it's going to have more of the liquid by the fraction of the distance to the solid. So that's the bigger one. You'll want to use the bigger side. If you were closer to the solid and you had a higher percentage of solid at that equilibrium point, then you would use the R, the smaller value. Okay, I'm going to give you one more example in this first part of chapter 9. We're going to do cooling of the same copper nickel alloy. And we're going to look at how the material changes and goes through different changes with our phase diagram. So in our same copper-nickel system, and we're going to use our same value of 35% concentration of nickel by weight, and we'll start at a 1300 degrees Celsius, so we're at point A. And we're going to consider the microstructural changes that accompany with the cooling. So if we're going to take it down to, in this case, from 13 down to 1100 degrees C, we're going to see some changes. At A, we are 100% liquid. There's one phase present. We know that we have 35% nickel in that solution. All right. When we hit point B, we've cooled down to B, whatever the temperature is at that point. We're right on the boundary line between being all liquid and not all liquid. And so we start to nucleate out little parts of this nickel copper alloy as a solid. And from there, from B to D, we have present both liquid and solid. But at this point, we're at the very beginning with tiny little nucleation sites that are basically by weight not significant. When we cool down to point C, I'm going to put these in here. B and A is up here at this temperature. Point C, we have both liquid and solid present. Those crystals, or those nucleation sites have grown. They're larger now. And we can use the lever rule to determine what is the composition. I'm sorry, not the composition, but the mass fraction of both the solid and the liquid. And we can use our isotherm intersections with the solidus and the liquidus lines to determine the composition of each of those phases. All right, so this is our rule number 2 in this case. All right, when we cool down to D, we are now at the boundary between all solid and liquid. So we are nearly all nearly all solid. And in this case, I think there's probably too much green showing for this one, where it should be nearly none. It should be almost completely blue. But at this point, we have our line, and we can connect and know that we have 24% by weight in the liquid, 24% nickel that's in the liquid, and we know that we are like nearly 36%. So you're like at, just 1% weight nickel in the solid. And then once you move down into point E, you've hit 100% solid. It's all at equilibrium with a one-phase system, and we know that we are back at 35% by weight nickel. Now, I want to point out here, I want you to think about, we're going to wrap up this first section. I'm going to erase some stuff for a second. Okay, now that's wrapping up. What does this mean? How do you use it? But now I want you to consider the effects of this behavior on the final cooled solid material. All right? And I want you to think about it spatially. So between now and when you start part 2, I want you to think about each of these nucleation sites and the concentration of nickel at that point. And then as that point grows, I want you to think about how the nickel, the percent composition of nickel is changing as this material cools from a liquid to a full solid. And what is the gradient effect thereof within each crystal of this material? Okay, so that's your hint for today, and this will be the end of part 2. Or part 1, sorry. Phase diagrams. So happy thinking on that.